Sitting on top of this Falcon 9 rocket at Launch Pad 39A at the Kennedy Space Center is NASA's latest instrument that will be sent to the International Space Station. It's called Sageiii, and it will be used to monitor and measure something that is important to the entire human race and every other living thing on the planet: Earth's precious atmosphere. For many of us in the general public, this looks like just another one of the hundreds of launches that we've seen NASA perform over its 50-year history. But for the scientists, engineers, and support staff who have spent years of their lives preparing for this moment, this launch represents the culmination of all their efforts. It is impossible to calculate how much planning, execution, and sacrifice this team has made to get this instrument to this point. But suffice it to say, there have been many sleepless nights and long hours getting everything just right. So it's easy to understand why so many of these engineers and scientists are holding their breath at this moment. Although this is not the first Sageiii instrument to go to space, it is the latest and most complex, since scientists first realized that Earth's fragile atmosphere was thinning further and in need of monitoring. Because this mission is so important, the tension is high for the Sageiii team. Have they checked everything? Will the rocket work? Will this mission be successful? They will know in just a few minutes. On this episode of NASA X, we will go back and look at why the Sageiii instrument was developed and get a better understanding of what it will be monitoring. We will also follow some of the team as they prepare the instrument from the beginning to shipping, to the clean room, and eventually into space. And we will be there for the launch to see if everything went as planned, or if it reaches its final destination attached to the International Space Station. Here in this building at NASA Langley, some very important cargo is being loaded aboard this truck for a special delivery. Inside this container is the Sageiii instrument that has been designed to study aerosol distribution in our atmosphere and to study ozone, which is a gas found in the upper atmosphere that acts as Earth's sunscreen. This cargo's first stop is NASA Kennedy Space Center, but its ultimate destination will be 250 miles above Earth, attached to the International Space Station. More than 25 years ago, scientists realized there was a problem with Earth's protective coat of ozone. It was thinning. So NASA and the world community worked together to send instruments to space that could help us better understand what was happening in the atmosphere. Beginning in the 1970s with the Stratospheric Aerosol Measurement SAM instrument, then SAM-2, Sageiii, Sageiii-2, Sageiii-3 Meteor 3M, and now Sageiii ISS have all been invaluable in helping understand Earth's aerosols and Earth's thinning atmosphere. The Sageiii family of instruments was pivotal in making accurate measurements of the amount of ozone loss in Earth's atmosphere, and also played a key role in measuring the onset of ozone recovery resulting from the Montreal Protocol, which was passed in 1987. Even after 25 years, the Sageiii instrument is still the best instrument for the job, and now, with updated hardware, NASA is preparing to send the third generation of the instrument into space, this time attached to the International Space Station. But before it can be placed on a rocket bound for the ISS, Sageiii will have to be retested, making sure any components were not damaged during its journey from Virginia to Florida. That work is being performed in a clean room here at NASA Kennedy's Space Station Processing Facility. The team will go through procedures to make sure that Sageiii is in perfect working condition.
This week the team is working to complete the full functional test of the instrument payload. And what that does is it verifies the instrument's, the subsystem's functions and also the test the interfaces between the subsystems. And it's in the clean room because we have to meet contamination control requirements. And those requirements are really important because we do not want any of these, the optical or the radiator surfaces could degrade over time if there's surfaces are contaminated.
To fulfill its scientific goals, Sageiii 3 is equipped with a set of tools with a total mass of about 1,162 pounds. Its most important payload is the Sensor Assembly Instrument, a grating spectrometer that measures ultraviolet and visible light and has a 2-axis pointing system. The Sensor Assembly Instrument contains the Charge-Coupled Device Array Detector that enhances measurement capability and may allow for new experimental data products like methane, bromine monoxide, and iodine monoxide, as well as measure larger aerosols. Sageiii 3 is also fitted with the Interface Adapter Module, which is characterized as the brain of the instrument payload, the Disturbance Monitoring Package, the Hexapod Pointing System, and the Instrument Control Electronics Box, while the Hexapod Pointing System will act as the legs of the payload, keeping the instrument level in orbit.
Basically, we're exercising all the parts of the payload. We'll do all the things that we're expected to do on orbit. We'll take science data. We have a light source simulator that we use to simulate the sun, and it allows us to take science events. We'll move the hexapod, we'll move the upper platform to different locations. We do a range of motion tests just to make sure that it can cover all the extremes of its envelope. You know, we have some redundancy, so we'll check the main side and the redundant side and make sure we can do things like upload software and run certain commands. Pretty much putting the payload through its paces. And we've done this several times along the way, and then we'll take the data and compare it to the previous tests we've run and make sure that everything is in line, all the data is consistent, and we're getting the results that we expect.
When final power testing was completed, the instrument payload and the Nadir viewing platform were handed over to SpaceX for installation into the Dragon trunk of the Falcon 9 rocket, leaving the Sageiii 3 team waiting for a launch. Even with Sageiii 3 in the hands of SpaceX, the team continued to go through scenarios preparing for an eventual home on board the ISS.
When we first get mounted to the space station, we actually will be running out of here 24/7 for approximately the first 2 weeks as we power on each subsystem. We've got 5 subsystems, so we power each one up about once a day just to make sure it powers up correctly, check the status of it. And then we'll be doing calibrations, make sure the CCD, which is kind of a fancy digital camera, the main part of the instrument, is calibrated correctly, it points correctly. So we'll be doing that all out of here about 24/7 with a crew of about 8 of us. And then once we finish the commissioning phase, then we'll go more into the routine operations where on a daily basis we'll have someone come in here, they'll check the health and status of the payload, send the commands up that we need to make sure it's executing correctly. And then we'll be based in another building here at Langley. We'll be down at Kennedy. I'm very excited, so I'm going to have our whole mission ops team down there, and we'll watch it launch, and then we'll hightail it back here very quickly. It'll take about 2 to 3 days for it to dock to the space station, and then once it's docked there, the space station has about up to 30 days to actually pull us out of the Dragon trunk of the SpaceX launch vehicle and install us on the outside of the space station.
After arrival at the ISS, Sageiii 3 will be robotically mounted externally on the station without the need for astronauts to perform a spacewalk. The instrument will orbit between 239 and 257 miles above Earth's surface at a 51.6-degree inclination with nearly a 3-day repeat cycle. This is important because the station's orbit is expected to help maximize the scientific value of SAGE 3 observations. The main scientific objective of the SAGE 3 mission will be obtaining high-quality global measurements of key components of Earth's atmosphere. In particular, the instrument will assess the state of recovery in the distribution of ozone and will re-establish the aerosol measurements needed by both climate and ozone models. The view from the space station will give researchers a new perspective of atmospheric composition and will allow scientists to monitor the health of the ozone layer and track recovery of stratospheric ozone since ratification of the Montreal Protocol. Researchers are hopeful that if the predicted models are true, that by the mid-2020s, ozone will have recovered about half of the amount lost from the pre-1980 levels. Other than ozone, SAGE 3 will also help to reinstitute aerosol measurements, crucial for more accurate long-term climate and ozone models.
Ozone's really easy to explain because it's a chemical. Aerosols are different in many ways. The clouds are aerosols, dust is an aerosol. Volcanic eruption produces ash that's an aerosol, but it also puts gases that convert to sulfuric acid. Aerosols are anything but predictable. So what you measure when you look at aerosols depends upon how you look at them. If you do it with a LiDAR system, you measure one parameter. We use occultation. We also use limb scatters, two different ways. And those two things combined allow us to look at composition a little bit, phase a little bit, but we're looking at the overall the size distribution of the aerosols, and so what we're really trying to get at is how much mass there is in the aerosol and what the surface area density. Those are two important properties for modelers to use. So the aerosols that we're looking at are in the stratosphere, and the primary effect there is when say a volcanic eruption goes off and you see these beautiful sunsets. That's one thing that people can immediately connect with, but it's like adding an extra blanket at night on a cold night. It will prevent some of the radiation from leaving. The aerosol layer itself heats up a little bit, but it's also like putting on a bit of sunglasses as well. On the surface, you get a little bit of a cooling. Very subtle effects, but if you're looking at the long history of temperature change, say on the surface, you're going to see a lot of variability in there, and that's often highly correlated with the amount of aerosol.
The sulfur dioxide, once it gets into the stratosphere, all the big rocks and everything, that's regional. It gets washed out, pushed out, whatever. It gravitates out locally. Stuff that we're looking at is the SO2 that gets in the stratosphere, changes to sulfate particles, condenses and forms micron size or less sulfuric acid droplets. As the sunlight's coming in, those particles absorb some of the radiation and scatter back some of the radiation. These little micron-sized particles or less. So the scientists are going to be happy about getting the aerosol data in case we do have another volcanic eruption. But then ozone, it makes the gold standard ozone profiling, and they're all waiting for that because we want to see if it's recovering. You know, it's all tied together. So we're not only going to check the trends of ozone, but we're going to be able to be up there for the aerosol and studying aerosol.
Moreover, if there are any new changes to the ozone layer, the data will help the scientific community identify the cause and assess the impact of the changes. Understanding the stratospheric ozone changes is crucial to determine whether the recovery of the ozone layer is progressing as expected since the Montreal Protocol was enacted. After all their hard work, the day the team has been waiting for has finally arrived. Launch day.
T-minus 1 hour, 15 minutes.
Although most are confident, launches can be stress-inducing. Thousands of hours and millions of dollars have gone into this effort, and for now, everything is out of their hands while SAGE 3 attempts to make a perilous journey from Earth into space.
So today is kind of like the ending of one chapter and the beginning of another chapter. So all the work that we've put in to go ahead and prepare the payload for launch and for on-orbit operations and for processing the science data, those have been complete. And so we've successfully integrated our payload into the Dragon trunk. And so we're here at Launch Pad 39A. It's a Chamber of Commerce day, historic 39A, and we're looking forward to launch at 10:01 this morning. And I'll be honest with you, it doesn't get much better than this. And the reason I'm so happy, and hopefully it's coming through, is that our team has just been so exceptional in that they've gone ahead and taken care of every detail. And when I go ahead and go to bed at night, I don't lose any sleep thinking, did we miss something? I think the payload we've designed and built and tested is about as perfect as we could make it. And I think it's worthy to go ahead and continue the SAGE data record. And that's what we've worked so hard to do. Because if you really look at it, the Montreal protocol appears to be working. The decline of the ozone has stopped. And so if the models are correct, the ozone layer should recover by mid-century. And so what we'll do is, with SAGE on the space station today, we'll make measurements of the ozone layer that will help scientists go ahead and assess the state of the recovery. And I think that's worth working pretty hard to do, because I think that's important to every person on the planet. The other thing that we do is we measure aerosols and some other gases. And so the aerosol measurements continue a long-term trend, developed with the SAM experiments in SAGE 1 in 1979, SAGE 2 in 1984. The SAGE 3 we flew on a Russian Meteor 3M satellite in 2001. And so that data is a good long-term stable trend baseline that can be used by the science community. So, man, we're ready to go. Ready to go ahead and complete the installation, which is done robotically. I kind of look at that and I go, when I was a kid, the idea of an orbiting laboratory and then a rocket without a human driver and then robots basically taking care of the assembly on orbit, that was all science fiction, and that's like complete fact today. And so we're kind of on the cusp of ready to go off and do that. And it's like, wow, okay, this is cool. Our team is ready, the hardware is ready, SpaceX is ready. The weather, I don't think it could get any better than this. So I think we're ready to go.
As crowds gathered and the SAGE 3 team anxiously watched the countdown clock, an event typical in many launches occurs. A delay.
Hold. Just had a hold in the countdown.
Fortunately, the problem was addressed quickly, and early the next morning, SAGE 3 was on its way.
3, 2, 1. Ignition and liftoff of the Falcon 9 to the space station.
Soon after it arrived at station, the instrument made its way to its final position, and the team began receiving valuable data so important for the entire human race. The instrument continues to work perfectly, with data streaming in, adding to the global database of information about our atmosphere. This data is not just being studied at NASA, but is being made available to researchers around the world as well, helping us keep an eye on our fragile atmosphere. After years of hard work by so many dedicated people, this mission is a success. From humble beginnings in 1979, the SAGE saga has evolved into a state-of-the-art instrument capable of providing data that will be useful 50 years from now. NASA will continue to build on the success of SAGE 3 and share the journey of scientific exploration with the world.